René Descartes, at the court of Queen Christina of Sweden. When Descartes went to Sweden in 1649, he was 53 years old and well established as a philosopher, scientist and mathematician. He was known throughout Europe and his writings were widely read. In the history of mathematics, Descartes has a principal role to play, as we'll see shortly. But standing behind Descartes in this purely imaginary group scene is a figure who arguably is central to the development of scientific and mathematical thinking in the early part of the 17th century. His name is Marin Mersenne. We start our story in Paris in the 1630s. Mersenne is a friar in the Mennonite convent of the Annunciation. The Mennonites, as the name implies, are a relatively small and humble order, but they have built for themselves a reputation for scientific investigation, with Mersenne amongst their most celebrated experimenters.
Amen.
Mersenne himself made a study of the nature of sound. His love of music made this a natural choice for his inquiring mind. But it was a subject not much studied at that time, and Mersenne was one of the first to do so. He discovered, by experiment, that the pitch of a plucked string is affected by several factors. First, it was proportional to the square root of the tension. Secondly, it was inversely proportional to the length. Thirdly, it was also inversely proportional to the square of the diameter. This formula was Mersenne's own discovery. It was completely new, and actually contrary to the accepted Pythagorean view of the relationship between tension and pitch. But Mersenne wasn't content with just an experimental determination of this relationship.
But why should this law hold? How can I prove mechanically that this law must hold true? I know that it is true to within the limited precision of my experimental observations. But can this formula be proved with the certitude of a mathematical explanation? The tension governs the movement of the string. But what is the nature of this movement? I have determined, using very long strings that vibrate very slowly, the manner in which the string behaves. But what are the physical laws that determine the manner of this vibration and related to the tension? And what are the harmonics of a plucked string? Without changing the length or the tension or any physical aspect, I can cause the string to behave differently. And produce notes of several different pitches. Now this I find puzzling enough, but I have listened deeply to many notes, and I have determined that plucking an open string can produce as many as 5 different tones at the same time.
This constant questioning of phenomena is characteristic of Mersenne's work. During his lifetime, he performed experiments in sound, optics, heat, hydraulics, ballistics, and much more. And Mersenne didn't keep his work to himself. He meticulously wrote up his researches in books and letters. Indeed, his letters alone run into thousands of pages and are at least as important as his books. For Mersenne chose his correspondence carefully, passing on questions and results to all the most capable people of his day. It was said that to inform Mersenne of a discovery meant to publish it throughout the whole of Europe. For Mersenne had a mission.
It is my role to be an instigator, to create problems, to provoke quarrels even among the scholars. And out of this, the truth must emerge. Intellectual collaboration is a duty. Unfortunately, scholars are stubborn, often selfish people. To their disgrace, they will not share their discoveries. I myself have scrupulously followed the rules which I proposed and promoted science in all places. I pose problems always with the idea that others may work in collaboration to resolve them. I've recounted my experiences and experiments in the minutest detail so that others may take them up and, if possible, improve upon them still further. Thus it is with a certain impatience that I strive to form a truly international academy of science. Time is pressing. Good opportunities are being let slip. This century has produced many good minds which are capable of adding to the sciences and may be capable of reforming them in many ways. If only they would be more open with the results of their researches.
Typical of many scholars of the day was the secretive Roberval. Roberval became professor of mathematics at the Collège de France in Paris in 1632, a post he held for the rest of his life. One reason for his secrecy, and why he didn't publish many of his results, was the fact that he had to compete for his post every 3 years. So his original methods he kept to himself. A famous problem of the time on which Roberval worked concerned the nature of the curve called a cycloid. A cycloid is formed by following a point on the circumference of a rolling circle. It's an elegant curve and was often used by architects. This is the Ponte di Mezzo in Pisa. Built by pupils of Galileo, it has cycloidal arches. But despite the elegance of the cycloid, little was known of its properties. For example, could it be that one of its arches was no more than half an ellipse? Another outstanding problem was to find the area under a cycloid. To solve this problem, Roberval cleverly exploited a technique using indivisibles. First, he considers only half the cycloid. He now sets about finding this area. This curve is generated by half a revolution of a circle. So Roberval divides the generating circle in half. What he's going to do next is subtract the area of the semicircle from the cycloid. The indivisible concept of area means considering the area of the semicircle as if made up of horizontal parallel lines. To subtract the area of the semicircle, each line is moved parallel to itself inside the half cycloid. The area of the half cycloid is now divided into two parts. The shaded part is equal to the area of the semicircle. That's a half pi r squared. Now Roberval has to find this area. By another clever indivisible argument, he shows that if you take a copy of this shape and turn it over, then it fits exactly with the original to form a rectangle. The area of this rectangle is easy to work out. Its height is the diameter of the generating circle, and its width is half the circumference of the circle. So the area of the rectangle is 2 pi r squared. So the area of half of the rectangle is pi r squared. That gives the area under half an arch of the cycloid to be a half pi r squared plus pi r squared, which is 3/2 pi r squared. So the area under one arch of the cycloid is twice this. That's 3 pi r squared. In other words, the area under one arch of the cycloid is 3 times the area of the generating circle. Roberval had many ingenious methods like this for solving problems on areas of curves and for finding tangents, but alas, he kept them secret. Mersenne worked hard to break the secrecy and isolation of scholars of the time. In addition to the huge correspondence he maintained, he also formed and attended gatherings in and around Paris of scholars and scientists. But of all the scholars, it was the mathematicians that Mersenne regarded most highly. In 1635, he writes to Peiresc about one of his scholarly groups.
I have been assured that we shall have Monsieur Gassendi here at the beginning of June. I'm very pleased about this. He will see the most noble academy in the world, which has recently been formed in this town. It no doubt will be the most noble, for it is wholly mathematical. As for the names of the most excellent gentlemen who attend, they are Messieurs Etienne Pascal, Midorge, Hardy, Roberval, Desargues, the Abbé Chambon, and others. My good friend René Descartes does not attend. He will not commit himself to any group and is contemptuous about ideals. But I continue to correspond with him and he with us.
Thus Mersenne created and became the center of a scientific community that stretched the length and breadth of Europe. Mersenne, however, was not to see his ideals of international academies come into being in his own lifetime. But shortly after his death, the French Academy of Sciences came into existence, with many of Mersenne's circle of correspondents, including those from countries other than France, among its early members. However, one of the most important mathematical advances of the century was to come from the pen of René Descartes. Descartes had been studying mathematics for some time, when in 1631 he tackled the solution of a classical Greek problem. He proudly boasted that he solved it in 5 or 6 weeks. But it wasn't so much the problem itself that was important, but the entirely novel method of solution. What Descartes did was to set up the foundations of the system which we use today for the examination of curves and graphs, and which bears his name, Cartesian geometry. The problem tackled by Descartes is known today as Pappus' problem. We start with 4 fixed straight lines. From a point C, distances are measured to these lines at given fixed angles. The problem is to find all the positions for the point C for which this equation holds. The product of the distances d1, d2 must equal a constant multiple k of the product of the distances d3, d4. Pappus says that the point C may lie anywhere on some particular curve, and furthermore, that curve must be a conic section. But how to prove it? What follows is more or less Descartes' proof in his own words.
Since so many lines are confusing, I simplify matters by considering one of the given lines, and one of those lines to be drawn, as principal lines. To these lines, I shall try to refer all others. Let x be the length of this line segment, and let y be the length of this line segment.
What we see here is the birth of coordinate geometry. Remember, the line segment y must meet the line segment x at a given fixed angle, so a pair of values for x and y will determine the point C uniquely and unambiguously. Descartes now proceeds to express every distance in terms of x and y. For example, the distance of C from the third fixed line is cy over z plus bcx over z squared, where c, b, and z are fixed constants, determined by the positions and angles of the 4 starting lines. Expressing all distances in terms of x and y, and using the original equation, Descartes arrives at the following conclusion.
To find a position for the point C, we assign a value to x. Corresponding to this value of x can be found by solving an equation of this form.
In other words, a position for the point C may be calculated without any reference to the geometry of the original problem. Instead, it's found by solving an algebraic equation. Descartes continues.
If we then take successively an infinite number of different values for the line segment x, we shall obtain an infinite number of values for the line segment y. And thus we can find an infinity of different points, by means of which the required curve can be drawn.
What's crucial about this solution is first the use of algebraic manipulation to solve a geometrical problem, and secondly, the complete generality of the method, which applies, as Descartes observed, equally well to problems starting with more than 4 fixed lines. In Descartes' words,
This method takes the best traits of geometrical analysis and algebra and corrects the faults of the one by the other.
it was the tremendous power of this method that was to reshape geometry. It quickly spread throughout the scientific community in Europe, where it got used, improved on, and helped to establish the language for modern science and mathematics. But producing revolutionary ideas in geometry was no guarantee of fame. Girard Desargues was a much-respected member of Mersenne's mathematical group, an engineer who later became an architect. He was an expert in classical geometry with a particular interest in perspective drawing. His earliest surviving publication is a pamphlet on perspective published in 1636. It is for the most part devoted to construction that an artist could use to create a picture in correct perspective. But Desargues was to follow this work with a book on conics. When Descartes heard that Desargues was at work on such a book, he was astonished.
I can hardly imagine what he can have written concerning conics which can be good. It is easy to explain them more clearly than Apollonius or any other, but it seems to me very difficult to say anything about them without algebra, which could not be done much more easily with algebra, as I myself have pioneered.
But Desargues had indeed done something quite revolutionary. What he did was to look for properties that were common to all the conic sections. He considered the ellipse, the parabola, and the hyperbola. With a change of viewpoint, he observed that all these conic sections could be made to line up behind each other. And from here, they all looked like sections of a circle. Now, what Desargues wanted to know was, were there any properties of conic sections in general that remain unaltered by this change of perspective? The apparent length of a line obviously changed when the viewpoint changed. So too did angles between lines, but at least straight lines remained straight lines. And Desargues did indeed find several extremely important properties that remained invariant by a change of perspective. A simple one that we can derive from Desargues' work is this. Given a line xy, we say that the points A and B divide the line internally and externally in the same ratio if the length xa divided by the length ay is equal to the length xb divided by the length by. To Desargues, there are 4 points in involution, and his methods show that they survive changes of perspective. Apollonius had called it a harmonic ratio, and it crops up all over the place in geometry. For example, consider an ellipse and a point B. From B, we can draw 2 tangents to the ellipse. Label the points where the tangents touch the ellipse, P and Q. Now draw a line through PQ. 4 points in involution occur if we draw any line through B, cutting the ellipse. The 4 points B, X, A, Y are 4 points in involution. And this is a construction that survives a change of perspective. However we look at the diagram, as a circle or as an ellipse, the points B, X, A, Y remain 4 points in involution. What Desargues did then was to take those theorems of Apollonius that had been treated separately for circles, ellipses, parabolas and hyperbolas, and show, using his invariance of points in involution, that there were in fact completely general theorems on conics, of which the theorems of Apollonius were special cases, as Desargues noted at the end of his paper.
Some of my theorems and their consequences contain several of the conic propositions of Apollonius, and leaving aside the lemmas, 4 of my theorems contain the entire dissection of the cone by the plane.
Boastful? Maybe. But there was a great deal of truth in it. Mersenne and Descartes both appreciated the genius of Desargues, but few followed up his line of thought at the time. One of the few who did take up his methods, however, was the young Blaise Pascal.
Monsieur Desargues is one of the great minds of this time, and one of the best versed in mathematics, including conics. I must confess that the little I have found on these matters I owe to his writings. I have tried to imitate as much as possible his method on this subject, which he treats without the use of a system of axes.
Following the methods of Desargues, Pascal discovered his famous theorem about the hexagon. Take 6 points on a conic section. We'll use a circle, but any conic will do. Now find the intersections of the lines joining opposite pairs of points. Pascal's theorem states that these 3 points lie on a straight line, and that remains true wherever we choose the 6 points on the circumference. In this position, we produce 3 parallel lines. The point of intersection now jumps to the other side. The theorem even holds true in this position, if we take the 6 points out of order. Pascal's proof is lost, but it almost certainly starts with the circular case, and then extends to the other conic sections, following the projective methods of Desargues. Unfortunately, Pascal was an unhappy figure, torn between mathematics and religious contemplation. Much of his mathematical work has been lost. His treatise on conics, inspired by Desargues and written in the 1640s, has vanished. As for Desargues' revolutionary ideas, though attracting a great mind such as Pascal, few took them up. Virtually all traces of his major work on conics vanished after his death. Only in 1846 was a handwritten copy of it discovered by accident in a bookshop. Then, surprisingly, an original turned up in 1950 in the basement of the Bibliothèque Nationale in Paris. We can only speculate as to why Desargues' work wasn't properly taken up and fell into obscurity. Possibly it was to do with his new terminology. Descartes, whose work enjoyed far greater popularity, wrote to Desargues as follows.
It is certain that your terminology has been invented with wit and charm, but it seems to me it would not have been out of place for you to use terms taken from arithmetic, as I did in my geometry.
Descartes wasn't being boastful of his own work in this letter. His advice could be justified. Cartesian geometry was, in Descartes' own lifetime, to become a standard mathematical method. Indeed, this third edition of La Géométrie, published in 1683, contains 100 pages of Descartes and over 400 pages of commentary and additions by de Boon, Van Scoten, and Hooder. In the hands of these mathematicians, the ideas of Descartes were developed far beyond the classical geometry of the Greeks. Cartesian geometry, as it came to be known, was a revolutionary new method and a source of inspiration for Leibniz, Newton, and many other mathematicians in the second half of the 17th century.